We have one final type of problems related to intermolecular forces. And on these, we're going to be looking at mixtures. So taking two different substances, say a formaldehyde molecule and a water molecule, and saying, can these two attract each other? And if so, how? All right. So we're gonna actually focus in here on water, which is this molecule, and formaldehyde, which is this molecule, and we're going to look at this mixture, two different molecules, in a few different ways. So I want to first look at what is the strongest intermolecular force between each pair of molecules. And I'm going to always default to looking for my strongest, so look for hydrogen bonding, then look for dipole-dipole, then look for dispersion, because these are stronger, right? So hydrogen bonding, I need a donor, which means one molecule has an OH, FH, or NH, and an acceptor, which means the other molecule has an O, N, or F. So let's take a look here. So here's my water molecule, okay, and if you need to, you can draw it out just to see it a little better. And I see, okay, well that has the OH, so I've got a donor. Do I have an acceptor, an N, or O, or F here? Hopefully you're starting to recognize the O's, the reds there. And so yeah, this would be a good acceptor right here. So if I have a donor and I have an acceptor, then I'm able to have hydrogen bonding. And as of today, that's the strongest intermolecular force we know of. So I can look for those and I can say, hey, I can have hydrogen bonding. All right. Now let's just say instead that I had like a water and then this methane molecule. And so I'm looking for hydrogen bonding first because it's strong. I have an OH. Do I have an O or N or F on this molecule? I don't. And I don't even have a dipole on this molecule. So the strongest between these two, even though I have this OH, the strongest possible attraction would be a dispersion force because they just don't have that much in common and there's no N, O, or F here. So just because you have water doesn't mean in a mixture that it can hydrogen bond with something else. So that's how I identify the strongest intermolecular force. Now I could, in this quadrant, draw that intermolecular force. So I've got my water and I've got my formaldehyde, and we decided that the O will be attracted to the OH here, right? So I could draw, let's just keep my formaldehyde here, and that O will be attracted to a water molecule. If I want to emphasize what's happening here, there's my intermolecular force. Here is my partial positive H, my partial negative oxygen, and that is hydrogen bonding that I just drew. I could also hydrogen bond on this other lone pair here, right? So I could put a second water attracted there. Bottom quadrant C, do I expect these molecules, we'll stick with these, water and formaldehyde, to mix well? So if they're going to mix, two things I might look for: their intermolecular forces are alike, and or their intermolecular forces are strong. So here, as I look at these two, they have a very strong attraction possible between them, right? So I'm going to say, yes, I do expect formaldehyde and water to mix because of the strong hydrogen bonding between them. So these are two things that I can look for a reason to mix, and these I would expect to mix because they have that strong attraction between them. Final quadrant, remember D is going to be probably the hardest quadrant. We go from easy to hard. So final quadrant, rank the molecules from high boiling point to low boiling point. So high boiling point, remember, is going to be strong IMFs. Low boiling point is going to be weaker, or big molecules down to small molecules. Again, you might have to sketch some of these out to figure this out. So let's take a look at this middle one here. Okay, I have three separate molecules. And so as I look at these, I can see that every single one of them is nonpolar. That's kind of the first thing I look for. And because they're all nonpolar, all they've got going on is dispersion forces. So they all have the same intermolecular forces. If you can remember, if those are all the same, what do I look at next? Now I'm going to look at size. If it's small, it's going to be easy to boil. If it's big, it's going to be hard to boil or have a high boiling point. So I'm going to rank these from smallest. CH4 is small. Its boiling point will be smaller than C3H8, and its boiling point will be smaller than C8H18, which is the biggest one. So from high boiling point to middle boiling point to lowest boiling point. And this bears out in everyday life. This is in your gasoline, this is octane. This is propane. If you have a propane tank in your backyard, it's a gas, but it can be compressed to a liquid fairly easily. And then this is methane, which we can also compress, but methane is a gas at room temperature, comes out of our stoves or in our furnaces. So we go from a liquid down to a gas as our intermolecular forces get weaker. So I've left you a lot to practice here. Take a look at some of them, bring questions to class, and you will get better at these the more that you do.